Okay, let's take a look at today's lesson. It's on accumulation and population density. I think we're pretty comfortable with the accumulation part. We've done quite a few of those type before. We've worked a little bit with population density. Today we're going to just kind of extend our work a little bit more with it. We've worked with population density when it had to do with density along a straight strip, a straight line. We've worked with that before. And if you remember what we did, so let's kind of draw it out. Okay. The first one is similar to one that we've done before, where we have a city located along a straight highway, has a population whose density can be approximated by this function. Okay, so we're along a straight highway, so I'm just going to kind of draw that. Where x is the distance from the town square. We'll make the town square right there. Measured in miles. And our density function, p of x, is measured in people per mile. The town extends 4 miles on either side. So, and it tells us, kind of gives us some information from -4 to 4. Okay, find the population. So, when we are dealing with just a straight segment, what we do, and I'm just going to kind of write some information. Hopefully this will help. So population on a segment is going to be equal to density times the length, and I think I was in length of the segment, or the interval. So population on a segment is density times the length of the interval. Now, really abstract, I'm going to go back to really abstract with this because length of an interval isn't what we normally would think. If we are looking at this, we would call that delta x, change in x. That's what they're talking about of length. On a length on the segment is simply delta x, the change in x. So the density is going to be our p of x, which is measured in, let's see, where x is the distance from town, measured in miles. P of x is measured in people per mile. People per mile. Okay? Times the length, which is delta x. And what is delta x measured in? It's measured in miles, right? It tells us that this is measured in miles, times miles. So we can see that the miles go away, and I'm going to be left with the number of people. Now I'm doing this in a very abstract way because the one on the other page really confused people earlier today, and I'm trying, we need to tie them all together. So that's how we would do that. So we're going to basically, and we've done one like this before, we just integrated our p of x because the delta x in an integral turns to what? What is delta x in an integral? Dx. So it's built in. It's like we don't even have to think about it, this delta x. So in order to do this, we would integrate, and this is one where we have to go to either side from -4 to 4. Our function, which is the p of x, so that's the density function, p of x, which is 1500 times 4 minus x. And then our length of our interval is delta x, which is dx. So that's what we integrate. If it's just a strip, just a line, a segment, we can think of it as a segment. Population on a segment, which kind of doesn't make a lot of sense, does it? They're all in a line, but apparently they are all in a line. So we're in a segment. And what we would get would be 48,000 people. Okay, so that one is one we have done before. I just didn't go through all of the abstract reasons. Okay? And I'm setting us up for the one on the next page, which is much more complicated. All right. Now the second problem is on accumulation. We have water that's being pumped out of a holding tank. So it's going out of the holding tank, and this is the rate. Okay, it's important to note it's the rate. That's the rate that it is being pumped out. Our units are liters per minute, and T is in minutes since the pump started. So it's important to note that our equation, our formula, our derivative was created in terms of minutes. So we have to pay attention to that just in case maybe they give us time in hours or something. We just need to be sure that our units match. So the equation is written in liters per minute. So if the holding tank contains 300 liters of water when the pump is started, how much water does it hold 20 minutes later? All right, so we're starting with 300. That's our starting amount, and it's in liters, just like the equation is. Thankfully, we don't have to mess with changing units. So we have 300, and we want to take out the amount of water that's being pumped out in the first 20 minutes. So from 0 to 20, and we would integrate the rate, 4 minus 4e to the negative 0.12 t dt. This lesson is really going to require a calculator. Most of the problems are going to require you to use a calculator. And so we integrate that. We do 300 minus that, and we get 250.309 liters. And I'm hoping by this time most of us are really comfortable with the accumulation ones, that we're really comfortable with this. Are we okay on this one? Any questions? Okay. Let's go to the last one. That's the one that has been giving people some trouble today. So what I want you to remember here is this setup for the segment. How we set up the segment, the thought process. What our density is measured in. They tell us what it's measured in. If we kind of go with the units and pay attention to the units, hopefully it will make more sense how we come up with the formula. So let's go to our next page. Okay. So here we have a city that can be approximated by a circle of radius 8 miles. Moving away from the center of the city along a radius, the population density can be approximated by this function. Okay, so our density, let's talk about our formula. We're dealing with a circle now, a ring. We'll call it a ring. And I know some of us don't like talking about shells. Bless you. I know some of us don't like talking about the shells, but the shell method would help conceptualize what we're doing here. Because really we're looking at ever-increasing cylinders, like this inside here. So we're looking at circumference, ever-increasing circumference. So let's look at what, and again we're think cylinder, okay? Think cylinder. I'm going to take one of these strips and I'm going to open it up like a rectangle. And so it would look like this. And our circumference would be along the bottom. It would be 2 pi r. And this delta strip, what you would call it, or you think about the cylinder being opened up into a rectangle. This height is actually delta r, or whatever variable we're dealing with. Which maybe that's what students had trouble with earlier today. Maybe it seems like delta x or delta r isn't anything, but it is. It's basically the height of this strip. So if we're going to write an expression for really anything to do with this with a number of people, whether it's in this little shaded strip or whether it's just in the entire figure, we're going to, let me write this down. So population on a ring is density times area. Okay, so the population on a ring, let's talk about what the density is measured in. The density is measured in people per square mile. So it's people per miles squared, people per square mile. All right, so now let's talk about how, so that would be the function P of R. That would be represent our density. Okay. Our area is actually represented by this little strip that I've drawn right here, where 2 pi r is measured in miles. It's basically the circumference here. It's measured in miles. So this would be 2 pi r is in miles times our delta r, which is like our height, if you will. It's the height of this little strip, or width, whatever word you want to use. It's also measured in miles. So the miles cancel and I'm left with people. Now again, just like on the segment, remember on the segment how we had a delta x and that stood for miles? It was like a distance. What was the change in x was a distance. The delta r is like the change in r. It's like the distance. It's like the distance away, whichever distance we're looking at. So it is actually a distance. It's in miles. So this gives us our population in a circular area. And it looks very much like shells, doesn't it? On shells we had 2 pi r, r of x, h of x, but this is just going to be an r. There is no r of x to find. It's 2 pi r, which deals with the circumference, which again is a distance, and delta r, which is the change in r, which is also a distance. So that gives us our population if we're dealing with some kind of a ring. So this would be the formula that would find the number of people, the population. And so if we want to find the population of the city, notice how this equation is written as a distance from the center, moving away from the center of the city. Moving away from the center of the city along a radius, I'm using this population. So when I do my integral, it's going to be set up just like this. I basically have the 2000 e to the negative 0.15 r. That's my P of r. I have my circumference 2 pi r. My delta r is dr. The bounds, I have to pay attention to how it's written. It's written on a radius, so I need to do my bounds from 0 to 8. It's not written on a diameter. If it was written on a diameter, we would do negative 8 to 8. But it's written on a radius. That's what this is with respect to, is the radius. So we put that in our calculator. And we get 2 pi times 29988.687. And we realize that we can't have a part of a person. When I multiply the 2 pi times that number, I have to truncate the number. I can't like add a person to it, you know, we just need to truncate it. And so we should get 188,424 people. Okay.